Hello, Internet. Today I wanted to take a look at dot products. We've used them in the past, but I kind of want to step back and take a look at like the basics of how to use them and sort of what they are. So they're really useful. I think that's the why I like them so much. They're used in pretty much everything that you're going to do when you're talking about graphics or just 3D space in general. And there's so many uses for them. One of the things that I like using with them for is checking if something is like in front of you, or in a cone in front of you, or things like that, or just checking the relationship between two vectors. If you've ever tried in Unity to calculate like the difference between two angles, that's really hard in 3D space. Like traditionally, you just get a cosine or ArcCosine or figure out a way using normal trigonometry to kind of make that work. But once you start adding extra vector spaces, it doesn't that normal stuff doesn't necessarily work the way that you wanted it to, or at least not easily. And the cool thing is dot products kind of solve that, at least that very specific problem. So what a dot product gives you is it gives you the result of the cosine, the angle between 2 points. Not necessarily exactly that all the time. If you have two normalized points, it will give you the cosine between them, which can be really useful because then as soon as you have that, you can figure out if it's in a cone of whatever, or if something's in front of or behind. And that's just super useful for so many different things. So generally when we're using cosines, at least when I'm using cosines, I'm using it on normalized vectors, which means that they have each vector has a length of 1. That's important because the dot product is actually going to return part of the length of those. So if you have things that are not equal to a length of 1, you're going to get values that don't necessarily make sense when we're talking about them like this. So keep that in mind. Just if you don't know if they're normalized, normalize them, or just try to work in normalized vectors. But for the most part, I'll just create a script here, and we can kind of go from there. So what I kind of want to do with this project is create two scripts. One is just going to be a cone that's going to come out of some object, and the rest of the objects are just going to be gizmo drawers that are going to test if they're in that cone or not. And if they're in it, they're going to draw a different color than if they were outside of it. That's the entire project. So for this, let's do our cone tester. Sure. I never know good names for these kind of things, so we're just going to make it up. And so we get this, and we need two things. We need either an angle or a degree. So we can do like a public float cutoff, and we'll default that to like 0.5, I guess. So the way that like I mentioned, it was a cosine of what you were talking about, which means a cosine is going to start at 1 when they're both in line with one another, and it's going to go to -1 when they're both in the opposite direction of one another, and then 0 when they're not parallel, perpendicular to one another. So when they come at this angle, regardless of 3D space, so you know, any which way they feel like, then you're going to end up getting that. So parallel is 1, not parallel is -1, and then perpendicular is 0. And then you have the range between there. And so we can either convert into those correct angles that we actually want, or we can not do that. I'm going to close Netflix because it started playing a preview for something on my other screen, and that was super distracting. So 0.5 is going to be sort of half off. Think of it as 45 degrees. I think that should make sense. Yeah. So 45 degrees, we'll have an angle 45. Good. So if it's within 45 degrees, we'll have like this nice cone going, and it should just capture everything in there. And that is pretty much it. The way we're actually going to calculate these vectors is do a vector3 dot dot. And the way this works is you just give it a left hand and a right hand side vector. and then you're done. And so we don't actually just want to give it like this, that transform dot position and some other thing. Let's make this a little bit bigger. Some other thing dot transform dot position, because those, one, aren't normalized vectors, and two, it's hard to judge the relationship between them like this. So normally what I would do is I would subtract them and get a directional vector. So if you do it like this, it's actually going to get us the direction towards this transform, because we're subtracting this position. So we have 1 point and another point, and we took this one away, so suddenly we're over here somewhere, which means our vector is going that way, and we wanted it to go that way. So I think we should be able to flip these around. Let's do a minus there, and delete that one because that's not needed anymore. And then the other input, we need a normalized vector. And so what we're trying to do is see if the direction between the direction of the 2 points is equal to some normalized vector, or is it in line with some normalized vector. And so if we're trying to cast a cone forward, what we can do is we can take the forward vector of our projector, our current transform dot forward. And so that is the current forward direction. So for me, that'd be that way. And then we have some difference. So all those objects, we're taking where the object is, subtracting my position, and saying that's the remainder between us. And then we'll get a normalized vector that gets us a direction towards that object. And then we compare that to our forward direction. And then from there, we're going to get some output. And so if we normalize both of these, because we're not, I'm going to convert this to this. This will always be 0. That's fine for now. We're going to pretend like that makes sense. And so we're just going to get a normalized vector out of there. So there's 2 normalized functions. One of them is normalized, which is going to get a new normalized vector. The other is normalize, which actually normalizes the current vector. So if we had saved this into some direction, we could go direction.normalize. Normalize, there we go. And then that would be, the direction would then be normalized. So this is perfectly okay. That didn't do what I wanted it to do. Direction, there we go. So direction is what we want. And that would be the same as what I had previously. It's just a little different way. Depending on how you're working with these things, that one might make more sense. Generally, this one might be faster. In our current use case, it isn't. Because either way, we're going to be making new things. But the cool thing with doing a normalize like this is it's going to be an in-place normalize, so you're not making new objects. If that really matters to you, then go for it. I personally have not found many use cases where that's been my bottleneck, and so writing code that's easier to understand has been a better use of my time. So I'm going to go back to this one like so, and we can just forget this direction bit. And so the output of this is going to be a float, which is our cosine angle. And so we're going to get something out of there. This is getting very long, so let's split this up. Do that, and put this on a separate line. I don't know if that's easy to read or not, but it's there. Let's scroll up so you can actually see that now. And so this is going to get us a cosine angle. So this is going to be 1 if both are in line, if parallel, 0 if they're perpendicular. I spelt that right. I'm impressed. And -1 if they're reverse parallel. That's not an actual thing, but if they're going in the opposite directions, it's reverse parallel. That's what I mean by that. And so it's sort of giving us that meaning there. And then I need to remember trigonometry off the top of my head because I didn't look this up because I'm bad. So the actual angle that we have here is going to be a math f dot cosine. We want the ArcCos, right? So return the ArcCosine f, the angle in radians, whose cosine is f. So that's going to return us a set of radians. So we give the cosine angle here. And I'm going to change this to be 45 degrees. Like so. We're kind of doing this, like I'm separating this into two different parts. So this isn't going to make less sense than it will in like 5 more minutes. So what we're doing here is getting the actual angle out, but that's actually in radians, which I don't, they're great and all, but I don't like working in them. It's harder to remember parts of pi, so we're gonna just grab pi. That's not right. We're gonna do rad 2 degree. So rad 2 degree is a constant inside of Unity's math library that'll convert radians to degrees. It's just a constant value, some magic float. There's also a degree to rad if you want to go backwards, so you can kind of go in either direction. Unity has had, yeah, these are the values. So they calculated these for you, and so you just inject them into your formula. Hopefully not both in the same, because then you're not going to end up with anything that makes any sense. And then it doesn't like this. Okay, that's just a spell check error. That's fine. We can ignore that. And then we get our angle. And so what I want to do is, ooh, that's not right, is return if our angle is less than the cutoff. And so theoretically, if I'm doing this right, this is not the right function name. I'm going to change that. But if I'm doing this right, what we're going to do is we're going to take in a point, which we're going to replace here. So this will be our input point. We'll just add that up here, vector 3 input point. And then we're going to get the difference between those two, get the direction towards it, compare that to our forward vector to get the difference between that and the forward, and then convert that into an actual degree calculation, and then return true if that degree calculation is less than our cutoff. So if anything is less than 45 degrees away, we should say it's inside of this cone. So test cone. That can be the name of our function. We need to return a Boolean from this. And remove that comment because it doesn't make any sense anymore. And there we go. That's that. And so that is the entire cone tester. And now all we need is something to actually make this come alive a little bit more. So let's, just for the sake of making this super easy, let's add our cone tester onto our camera. I don't think there's an easy way to draw cones with the gizmos gadget, but we can make that up if we really want to. For this, I probably should. But for now, let's just skip ahead and do the next step. So, cone test object. That's probably not the not the best name, but we're gonna go with it. And so this is just going to be attached to an object, and it's just going to draw a gizmo of probably green if it's inside the cone and red if it's outside, because those are easy. So on draw gizmos, like so. We want that to be a mono behavior. And the other thing, I didn't want to delete that start method. Did I? We're doing gizmos here, so let's not do that in the start. Instead, let's do a private cone tester. I'm thinking of really, really bad, bad ideas that might actually work, but let's just keep this simple for now. So this will be our cone tester. That's in the name. And so if our cone tester is null, so if it hasn't been initialized yet, we'll just set that to null so everybody knows it's null at the beginning, and it just makes it a little bit nicer. Then, if it's null, then we're going to set it. So cone tester dot or equals game object dot find game object. What's the name of it? Game object of type, I believe. And so this expects a type, so we can just give it the cone tester as a generic type. And so this is just going to go in Unity scene and find an object named cone tester, or with the type of cone tester, and add that and return that here. It'll return the first one because we're just using find object of type. If you use multiple of these, you're going to want to have some way to select one or get all of them or whatever. So find objects of type is going to throw an error here because I'm expecting a single one. But this returns an array, which will just give you a whole set of all of the objects of that type in the scene. So that's one way to do that. We are going to assume that there's at least one, because otherwise we're going to null pointer, which is great. And so gizmos color equals cone tester dot what's the best way to do this? Test cone? Did I not make that public? I didn't. Okay, so we're gonna make this function public so we can actually call it, because otherwise that wasn't gonna work very well. And so we're just going to plug in our transform position. So just plug in our position. Get this. It really doesn't like what I'm trying to do here. So we're going to use a ternary operator, which is just going to be like an inline if. And so if true, we're going to do color.green. Otherwise, we're going to do color.red. And that's that. We aren't drawing anything though, so we should probably do that. So gizmos.draw sphere. Sure. We'll draw a sphere at our current position. Position with a radius of like 0.1. So this is radius, so it'll actually be twice the size because diameter is, yeah. So that's that entire thing. This is this entire thing. It's kind of bugging me that we don't, if our cone tester is still null, return. We might want to actually write out like an error message, but that should be fine for now. And so as long as we have this, we should be able to do our test cone. It should pull out this cutoff, and then this should just keep looping and only fetch it once, hopefully. So the first frame is just going to load a bunch of these. Then after that, it should be done. So theoretically, I can go and create a new game object, like so, add our cone test object, and we get this red sphere. And eventually, it will turn blue. Oh, that's why. It's not where I thought it was. There we go. So it is green here. And then as we move it down and get further and further away, it turns red. Maybe not the best example, but what we can do is create a lot of these. Brilliant idea. Let's do a cone spawner. And so what this is going to do, it's not going to spawn cones. I probably should have named it something else. But it is going to spawn a lot of things. So let's give it an int and say spawn number. We don't need an update. This is going to go away immediately. And we'll initialize this to like 100. I think this makes sense. With a float radius. And we'll say that's equal to 50. Kind of guessing at these numbers, but general idea here is we're going to spawn n number of things, wherever n is the spawn number. We're going to spawn a spawn number of things in a radius around whatever object has the script on it. And we're going to attach that cone test object to every single one of them. So for an int from I equals 0 to I less than the spawn number, so just our normal loop, we are going to create that. So we're going to grab our game object out of this, which is just going to be our spawned object, and instantiate some new object at some place. Actually, we can just use the cheat method and just do new game object. Done. And so we need to create a point to spawn this at. So spawned object dot position, dot transform dot position is going to equal a random inside unit sphere times our radius. And so that should get us a random point inside a unit sphere. So a unit sphere has a radius of 1, and it's just a sphere. So it's 3 dimensions with a maximum radius of 1, but it could be less than that. And then we're multiplying that by a radius. So we're turning that unit sphere into a sphere with a radius of whatever our radius is. And then we'll just put it there and do that, in this case, 100 times. And that should be that. We don't add our thing though, so we should do that. Spawned object.add component. And we want to add a cone. Does this work? I've never done this before. I've done this before, right? This might not work. We're going to pretend like it will though. So the way this add component works, adds a component class of type component type to the game object. So it should spawn this new game object, or spawn this new mono behavior and attach it to this spawned object for us. And that should be all we need to do. Or it could blow up in my face. That's fun. So let's see how that works. We're actually going to need the spawner though, because otherwise this really is not going to do what I want. So there we go. Cone spawner, and let's up this to like 500. Right, that should be plenty. And so we should get a whole bunch of these. We're in the game, so we're not going to see any gizmos. But if we go back here, we can kind of see we're casting this cone. Everything in front of us has turned green, and everything else is red. And the cool thing is we should be able to change this in real time because they're all referencing this cone tester. And so as we increase this, we can see other objects in the back there turn green until we increase this to pretty much encapsulate the entire thing. And then, yeah, more in the back we didn't quite get. But if we increase this to like 180, suddenly we've captured the entire scene because 180 in both directions is yeah, everything. So that's that. Now we can just give it a number, an angle, and go on from there. And so this is really useful for this, obviously, where you can kind of see what's in front of you. Like if you're trying to do a vision cone and you want to see if the player's in somebody's vision, this will do that. But you can do a lot of other things as well. Like if you're trying to do like a shotgun in a game, or an explosion, or just trying to see if like a camera can see somebody, or anything like that. I want camera seeing somebody is a little bit different, but this is sort of one of those ways where you can just kind of do that, and it's super easy. Like the actual math for this is none of this. It's like 2 lines of code, 3 lines of code if you count the question bit, and this I'm counting as 1 because it's actually just 1 and I wrapped it. But like there's not much going on here, and yet it's so powerful because this is something that if you tried to solve this like naively, it gets really hard really fast. I've done it before. Or tried. It didn't work. But it's not fun. This is fun because it's super easy, and yet you get something that is actually really cool. Like you can calculate like a spotlight, for example. That's actually a really useful way to do this. Is you can do like see if something can be seen. And I think we've done this before with our magic flashlight shader that we did like more than a year ago. So that's that. I'll leave it here though because I think this kind of gets the idea across, and hopefully it's something that you guys can play with. I'll put this code somewhere so you can go and grab it and tinker with it. But that's really it. There's not too much to this to make this work. and yet it's really powerful, and there's a lot you can do with this. I've used this to kind of test like, or I've used dot products rather to test like, how does a orientation of, in like a top-down shooter, how does an orientation of the like spaceship you're driving align with the axis that the player is pushing on the controller, and try to figure out if you should apply the thrusters or turn the ship, because you want them to go in the direction they're pointing with the controller, but you can't necessarily do that in like a spaceship or a car, because it doesn't make sense if a car just suddenly starts going the other direction. And so you can detect those differences with this, because you get this nice smooth curve of, here's the difference between the angle of the joystick and the angle and the orientation of the car. That's one of the examples that I would use, because I've used that in the past as well. But I'll leave it here. There's a lot of things you can tinker with. You can make this bigger. Speaking of making things bigger, I'm not going to leave it here. We're going to increase that to 5,000. And maybe crash my game. But oh, there we go. Cool. Oh, maybe crash the game. But that's it for here. There's a lot of objects. And yeah, we have a Discord channel. It's down in the description. You can come and join it and chat about games or software engineering or whatever else you want to chat about. And yeah, if you have other suggestions or feedback for me, you don't like this kind of video, or you want something more, or you want to see something new on the channel, or you have this cool idea that you want to share and you think we should build, let me know. I'd love to hear it. But that's it for this one. So until next time, see you, Internet.